The next system of interest is tower analysis. In the basic course, we lumped together the tower, tiers, and foundation together. But now, as we add some more granularity to our capacity checks, it is worth creating a separate tab for just the tower. And when referring to the tower, I'm talking about the walkway hump and the individual towers and tower saddles as one unit. When referring to a column or a tower column, I'm referring to just a single column. And I've used the different color codes here to show you the whole tower versus the separate walkway hump or tower columns in this graphic. In future lectures, we will discuss the design and associated checks for the reinforced concrete tower columns using ACI 318. However, in this lecture, we will look just at defining cable forces on a single tower column and along the walkway hump. And you can see on the free body diagram here, I've shown the main span forces, the horizontal PH hand main, and how that splits up, the PT hand main, how that splits up into its horizontal and vertical component, as well as the walkway forces in the horizontal and vertical component. And then along the backstay, you can see how there's going to be a force on the top of the tower column and the tower column saddle from the handrail forces. Each tower column will have a single handrail force, and then all of the walkway cables will contribute to the walkway hump forces that are shown below. That's why I've drawn that vector a little bit larger. These are going to be approximately equal, with the handrail cable being larger, actually, if there is 2 handrail and 2 walkway. But as there get to be more walkway cables than handrail cables, a larger proportion of the force is going to be distributed into those walkway cables. And also remember, we find our backstay forces with the belt friction equation. Remember from before, this equation is based off cable geometry, but the conservatism can be modulated using mu. As we increase mu, or the coefficient of friction, more force flows into the tower and less into the anchor. So we can start with the tower column forces in the horizontal and vertical directions. Tower column forces are going to come entirely from the handrail cables. The vertical force we can take as the sum of the vertical components of the backstay and main span handrail forces, and then divide by 2 because we assume that the total handrail forces distribute evenly into both tower columns. The horizontal force we can take as the horizontal component of the main span force minus the horizontal component of the backstay force, dividing by 2 for the same reason. We use absolute value here in the rare case that our horizontal force components in the backstay exceed that of the main span. And remember that our vertical backstay and main span forces are the sine of their respective angles, and our horizontal backstay and main span forces are the cosine of their respective angles. In order to convert from total cable tension to the total handrail component, like we discussed before, we just multiply by the ratio of the handrail cable area, the total handrail cable area, to the total cable area. Now for the walkway hump forces, we will go through a similar procedure, but leave out the factor of 2, because like I said, all of the walkway cable forces are transferred into the walkway hump. It's not just one cable per tower column. We can go through the same equations as above, but using alpha for the walkway instead of alpha for the handrail. And then at this point, we'll move on and revisit tower analysis in a future lecture to actually discuss the component design, the reinforced concrete design, and detailed checks of the tower components themselves.